Welcome to this paper presentation on machine learning as an effective new tool for assessing human performance during simulation-based training. This is paper number 20207 in the ITSIC program. And I want to share work that Danielle and myself have done on using machine learning in the assessment of surgeons. So at the Nicholson Center, we offer courses which teach practicing surgeons how to do robotic surgery for the first time. And they come to us to learn all the basic skills that they need to control the machine and to understand how to use all of the instruments. During that course, they go through a number of assessments. They use simulators to assess their performance with the robot, but it's all a simulated robot. They use dry labs to assess their performance when using the actual robot, but actively doing the exercise on some kind of physical device that's not tissue. And they use wet labs to use the real robot with tissue that is realistic, though not living. So it could be excised animal or human tissue. If you look at the videos that we collect of all these different assessments, you'll notice characteristics about them that imply how well that they could be assessed by machine learning. So if you look at the simulator, you'll see that there are very few objects in the scene. Each object has very good contrast to the ones around it. And when you launch a simulator exercise, it always starts from the exact same angle with the same lighting. If you look at a dry lab exercise, it's similar. There are also few objects. The contrast can vary depending on the background and the device that's chosen. And the angles and the lighting can also vary, but they're usually very similar. And then finally, if you look at the wet lab environment, you'll find that there are very many objects in the scene. The contrast is terrible because they tend to blend together, and it really takes an educated and practiced eye to see the difference between them. And then finally, the angle at which the camera approaches the tissue and the lighting that it has is different in every single instance of the exercise. So we present these videos to humans to evaluate, and typically we present them with the dry lab and the wet lab exercises, but not with the simulator exercises, which I'll explain on the next slide. When a human has to assess those dry lab exercises, they use a tool called the Global Evaluative Assessment of Robotic Skills, which has been validated by the community and is widely used for assessing robotic surgeons. They get a Likert score and a total Likert score that sums those up. It's nice because it's very explainable and it's an accepted standard. So those are the pros. The cons are it's very difficult to access experts to do these assessments over and over again every time you teach a course. The assessments are certainly subjective based on the opinions and the experience of the person doing the assessment. And they can be, we have shown them to be inconsistent from one person to another prior to doing inter-rater reliability exercises. The simulators have their own internal built-in scoring system that counts the number of seconds it takes to complete an exercise, the amount of movement that's done, the number of collisions, the number of drops, the number of mistakes that are done. So the pros are those measurements are very objective. They're always exactly the same. They're consistent, and the scoring entity, the simulator itself, is always accessible. So anytime you do an exercise, the assessor is there with you inside the simulator. The cons are that there's no real good gestalt that explains how well you did, and not a good explanation of why something was good or bad. It has been said of these simulators, as with other simulators and automated systems, that they tend to measure what's easy to measure more than what's important to measure. So for our experiments, we collected videos from 2 different exercises from the simulator. The ring and rail that you see on the top there, and the suture sponging exercise over a period of a year. In that period, we were able to collect 254 videos of those two exercises. And as part of a previous experiment, we had both the simulator score of each of those exercises, and we had a human watch them and score them to give us a comparative score using the Gears metric. Then those scores from both methods were categorized as either representing expert performance, intermediate performance, or novice performance. So those form the three classes that we're going to try to teach a software algorithm to match using deep learning or machine learning techniques. We asked ourselves, or the core question of this whole paper, is whether deep learning neural networks can do the same job that a human can do. Can they watch a video of an exercise, process the pixels, and come up with a measurement of the quality of performance, whether that performance seems to be an expert, intermediate, or novice? In our work a year ago, we already showed that the neural network can watch the videos and identify the objects that are in the scene. So as part of this study, we wanted to know whether it could identify the quality of performance. This 7-layer network is typically found in textbook books and courses about neural networks, convolutional neural networks. But if you want to do a real study, a real problem with video, you really need to use a much more complex network. And so a network that is built to handle video is usually not 7 layers deep, but something like 95 or 100 layers deep. These are represented by systems that are out there in the wild called AlexNet, Inception, VGGNet. All of these are custom versions of this very large network size that it takes to understand what's happening in video. And so that's what we needed to use for this experiment. To create those networks and host them and run them, we really had two choices. We could either buy all of the computing equipment and install it in our center, and then load the programming tools and configure them, then install the AI models in TensorFlow and Keras, and then after we've run them, do the analysis ourselves at the end. Or we could rent those capabilities from a cloud computing provider, which also provides the programming tools and cloud-based versions of the AI models that we need. And the analysis that happens at the end is automated and is done for us. And so, of course, what did we do? We went looking for a way to do this in the cloud with tools that were built and configured by experts in the field, rather than ourselves who are really experts at something slightly different. We looked at the major cloud computing providers to find out what they offered in this area. And there are other companies that offer these services, but we examined Google, IBM, Amazon, and Microsoft to see what they could provide towards analyzing video and giving us a classification for that video. From each one of those, we needed cloud storage where we could load up the videos and have them on their cloud networks. We needed cloud computation, which included CPUs, GPUs, and TPUs, which are tensor processing units. We needed cloud-based AI or deep learning neural network algorithms. We needed those services to have something called transfer learning and AutoML. Transfer learning is where they're mostly trained on videos from other sources like YouTube, and then specialized for the problem that you present to it. So it can cut the training time down from weeks of computation to hours if you have transfer learning. And we needed AutoML, which is essentially the assessment portion where it assesses dozens or hundreds of different variations on these network architectures and provides you the results from the best performing one. And then finally, we needed all of those tools configured to do video processing. And we found that all 4 services offered the first 4 of those capabilities, but only Google at the time of this study was offering all of those as applied to video processing. Now, before you can do the sexy part of deep learning, you have to do a lot of data preparation. Data that was collected for previous experiments is usually not in the form that you need it for the deep learning experiment you're going to do. And we found that we had to perform about 19 different conversion steps on the video files that we had collected from the simulator, and about 7 different transformations on the data records that were stored in Excel that was associated with each one of those video records. And those 19 plus 7 steps were not obvious at the beginning, so we had to go through experimentation and trials with a number of other steps before we figured out those were the minimum set required to make this work. After we had performed all those steps, we had 2,227 video clips. And a video clip is different than the video in that the full video for this suture sponge exercise, for example, is about 3 minutes long. And the video clips are 10-second increments of those full videos. Because of the way the neural networks work, they don't have the ability to, quote, watch a video for 30 seconds or a minute even. The way they're programmed, they can only process data and make sense of it from beginning to end for a few seconds. And so we chose to cut our videos into 10-second segments, which is rather long in the deep learning world. And that's how we ended up with 2,227 of them. 494 of them were the ring and rail exercise, which isn't shown here, and 1,700 were from the suture sponge exercise. And that's because the suture sponge exercise is much longer, and so there's more video clips within each one than there is in ring and rail. When you loaded up all of the suture sponge exercises, for example, the first thing that the Google software does is count the number of instances of videos that were labeled as expert, intermediate, and novice, or 3 classes, to determine if you have enough of each to perform training. And in this case, we actually needed at least 100 video segments in each of those categories. And we had well over that number to do the training that we needed to do. So that's the data that you start with, and you run it through the Google algorithms, and the most graphical output that you get are these plots of precision and recall. And this plot is for one of the sets of suture sponge exercises. The algorithm was able to achieve an average overall precision of 80% accuracy. So that means that 80% of the time, when we labeled something as expert or intermediate or novice, the algorithm could match that. It would come up with an answer that matched what the humans had assigned or what the simulator had assigned to those exercises. So that's pretty good. And the AutoML feature of this online cloud service doesn't run just one fixed version of the model against your data. It actually runs about 100 different variations of that model where it changes the parameters of the convolutional neural network and looks at the output, and when it has run all 100 of those, it returns to you only the results of the one that performed the best. And that's a lot of work that, had we been programming this on our own, we would have had to do that ourselves, which would have been very tedious. So we were encouraged by these kinds of results. We actually ran through the models multiple variations of the data that we had. So as I said, we had videos from the ring and rail exercise, and we had data from the suture sponge exercise. And for each one of those, we had scores from the simulator and scores from a human evaluator using gears. So there's 4 different variations of data that we ran through the model. Then we created another set where we combined all the videos from Ring and Rail and Suture Sponge into one pool, and we challenged the model to be able to label as expert, intermediate, or novice either one of the videos that might happen to show up as it would process through them. So what we found was that in the Ring and Rail exercises, when the deep learning algorithm went to match the simulator, it had about 85% accuracy in matching simulators' classifications of people. When it did the same thing to try and match human scores, it was about 83% accurate. For Suture Sponge, matching the simulator, it was able to do it about 81% of the time. And matching the human gear score, it was able to do about 80% of the time. That's the data from the previous graph, actually. So the reason that it's better at Ring and Rail than Suture Sponge, we believe, is because the Ring and Rail exercise is actually a much simpler exercise. So there's a lot less variation and a lot less complexity in what you see happening in the scene. Then when we combine both of those exercises into one pool, it lost a few percentage points, which you would expect because it's the same size of network, but it's being asked to do a more complex thing. I mean, essentially to put 2 different exercises into 3 different classes. So it's got to do roughly, twice as much differentiation, but it fell only to 78% matching the simulator and 75% matching the humans, which still is encouraging. Now, this is a very first try at this kind of assessment. And so we feel that anything that's in the 80% level is super encouraging because we're able to get very high matching levels early on in the experiment. Now, if you look at the computers that were required to accomplish what just happened, at the end of the experiment, we have information on how many computers and what kind of computers were used. And we know that these are 4 virtual CPU machines with 16 gig of RAM on each one, which costs about $300 each. And each of these has an NVIDIA Tesla 100 card, which has 5,000 GPUs and 640 TPUs on it, which costs $3,000. The purchase price of 13 of those is $46,000. Running those in the cloud, or essentially renting those from Google, it cost us just over $1,300 to do the job. So for one experiment, the rental price was 3% of what the purchase price would have been. And that doesn't count the human labor it would have taken to set up all of our own hardware and software. So that's a huge advantage to a research project where you probably don't need to buy the hardware for that research project, and where your project probably can't afford the price of all the hardware it would take to do this. So this is kind of the only option to many organizations that want to experiment with this. Now, we would much prefer that our networks performed in the 90 percentile range rather than the 80 percentile range. And after doing all of our experiments, I believe that's achievable if you look at about 6 different ways to improve performance. The first one is to adjust the threshold settings between novice, intermediate, and expert. In the paper, we describe how those thresholds were arrived at, but I don't think those thresholds are necessarily ideal and perfect. And I think that if we move those thresholds a little bit, we will get a more favorable balance between those that are assessed correctly and those that are assessed incorrectly. Number 2 is always in neural network training, get more data. If we had more than the roughly 2,200 videos that we used in this experiment, I think we would get much better performance. Imagine that we had 10,000 videos instead of 2,274 videos. That would be a much better data set to learn from. Number 3 we could cull out some video clips that weren't really helpful. So once you cut these exercise videos into 10-second segments, if you watch some of them, you'll see that the actions in some of these short segments are not differentiable between an expert and a novice when you're just moving an instrument across the screen rather than actually holding a needle and pushing it through material. So there are some videos in there that don't help differentiate between experts, intermediates, and novices. They actually take away from your ability to do that by using up processing power on a task that may look identical for an expert and identical for a novice. And it really challenges the algorithm to figure out why they should be in those categories. So we could manually throw those away. We could change the length of the training videos. You'll notice that I said that we kept our training videos at 10 seconds long, and that may be too long. It may be that 6 seconds would be better, or 5 seconds. I don't think less than that. You need a video that's long enough that what you see happening actually demonstrates something to do with a level of expertise. And if you make them shorter, you end up with more of those videos that fall into improvement performance method number 3 there about throwing away ones that don't show useful information. So we could adjust it, but cutting it down to 1 second, 2 seconds, 3 seconds, 4 seconds is probably too extreme. But 5, 6, 7 seconds might work just fine and result in having more videos. Step 5 would be to reduce the number of classes that you have to categorize these videos in. We used novice, intermediate, and expert because that's the traditional way that surgeons do assessments of performance. And it's usually what's presented in the papers. But we were teaching a course where our real decision point was whether this person crossed the threshold between passing the exercise and failing the exercise. So if we reduced the number of classes down to just pass-fail, then the algorithm would be more accurate than it is when it's trying to use 3 different classes. And then finally, we need to learn more about how the Google Video Intelligence AutoML service works. This service by Google is relatively new. And as I mentioned, they were the only ones even offering all the tools that we needed at the time of this experiment. And because it's new, there's very little documentation available on it. And there are also very few published papers about results from using it. And so we read everything that was available, and there's still a lot of information that we're not clear on because it's just not documented anywhere. For example, we chose to use a 10-second video clip. We don't know what the effects of that video clip is on the algorithm. We don't know if watching 10 seconds really results in it evaluating the last 3 seconds, or whether it's done all of its work in the first 3 seconds and kind of ignores the last 7 seconds. We don't know how it works. And it'll take some time before that information becomes publicly known and can help us improve the performance of this algorithm or future experiments. All right, our conclusions. We believe from our experiment that we've shown that 80% accuracy from these algorithms is possible with simulator video. We believe you could get similar accuracy with a dry lab exercise if you'd improve the contrast in the exercise. And dry labs is where this is really actually valuable. Having a machine learning algorithm that can watch simulators and give a score on a simulator video isn't really that useful because you already have the simulator internal software giving you a useful score. But in the dry lab exercise, that's where you always have to call on an expert to give you a score of performance. And if you could get a neural network to do that for you, then you could eliminate a lot of human labor that's tedious and generally not accessible when you want it. We believe that the wet lab images are still too complicated and too non-differentiable to use deep learning to process those videos and say something useful about whether this is an expert or a novice or an intermediate. We think that's not doable with the current level of algorithms that are available. Now, how does this apply to other areas than surgery? Well, in our research, we discovered that a number of athletic training and performance organizations are feeding videos of swimming, football, netball, and dance performances into neural networks to try to do roughly what we were trying to do, to watch these performances and highlight errors or highlight successful performance and use them to improve the performance of the people in the video. In a military context, this approach could be used for applications in military training. The top two are pretty straightforward. If you were to have a camera watch a soldier disassemble a weapon and reassemble a weapon with high contrast between the objects, that should be roughly equivalent to what we did and relatively approachable with neural networks. Watching target shooting and assessing the accuracy of that with a video camera and creating a score sheet and a running performance of a soldier without having to have an instructor there, that should be very doable too, as long as you create a scene that has high contrast. The lower two images, much more challenging. First, you would like to create video that has high contrast between the things you're interested in and the background that you're not interested in. But it's difficult, and everybody puts on camouflage specifically to thwart visual detection and visual sense making of what you're seeing. And so it was difficult in the combat medic example here to differentiate the two soldiers from each other and even to tell where their hands and their instruments are in this scene. And the background of grass, which matches their uniform, makes that even more difficult to assess. But I think it's possible to create scenes that have features more like the top two images, even in these combat medic and house clearing examples, so that a video can be assessed by a deep learning algorithm. Thank you very much for your attention. We appreciate what you've done coming to this virtual conference.